Imagine for a moment if we could communicate at the speed of light, what would that mean for us? We're talking about a speed that's so fast it can travel around the Earth 7.5 times in just 1 second. That's right. Light speed is no leisurely stroll, it's a cosmic sprint, clocking in at approximately 186,000 miles per second. But why is the speed of light so significant? Well, it's not just a random number, it's a fundamental aspect of our universe, a cosmic speed limit, if you will. Nothing, according to our current understanding of physics, can travel faster than light. And this limit shapes everything from the way we understand the universe to the way we communicate. Now, let's bring this concept closer to home. In our day-to-day lives, we rely heavily on communication technologies, from the humble telephone call to the complex internet data transfers. These technologies use signals that travel at a fraction of the speed of light. And, while these signals are incredibly fast, they're not instantaneous. There are delays, albeit tiny ones, but in a world that's increasingly interconnected, every fraction of a second counts. So the question arises, can we communicate at the speed of light? And if we could, how would that change our world? It's a tantalizing concept, full of possibilities and challenges. From the mind-bending realm of quantum mechanics to the practical hurdles of technology and infrastructure, the road to light-speed communication is a journey filled with intrigue and discovery. In this video, we will delve into the fascinating realm of light-speed communication, its possibilities and challenges. We'll explore why the speed of light matters, how our current communication technologies compare, and what the future might hold. So buckle up and get ready for a journey at light speed. To truly grasp the concept of light-speed communication, it's essential to first understand the speed of light itself. This cosmic speed limit is a fundamental aspect of our universe, setting the pace at which all information travels. Imagine the speed of light as a car traveling at a staggering 299,792 kilometers per second. In layman's terms, it's like traveling around the Earth's equator 7.5 times in just 1 second. It's a speed so fast that it boggles the mind, yet it's an integral part of the physics that govern our universe. This speed isn't just an arbitrary number, it's a constant, a rule that nature itself adheres to. It's woven into the very fabric of space and time. The speed of light is so crucial that it forms the backbone of Einstein's theory of relativity, which explains how the universe works on a grand scale. But why is the speed of light what it is? Well, that's a deep question. The speed of light is determined by two fundamental constants of the universe: the permittivity and permeability of free space. These might sound like complex terms, but essentially they describe how electric and magnetic fields interact in a vacuum. And this is where things get interesting. If you could alter these constants, you could, in theory, change the speed of light. But doing so would also change the fundamental properties of the universe. It's a bit like trying to change the rules of a game while you're playing it. The game itself would become something entirely different. So, bearing in mind the incredible speed of light, let's now explore how this impacts our current modes of communication. As we shall see, the speed of light isn't just a cosmic speed limit, it's also a limit on how quickly we can share information across vast distances. And in a universe as vast as ours, that's a limit that has profound implications. From radio waves to fiber optics, our communication technologies are bound by the speed of light. This cosmic speed limit, faster than anything we can currently achieve, dictates how quickly we can send and receive information. But let's break it down to understand it better. First, consider radio waves, an invisible form of light that carries our favorite tunes, news broadcasts, and even television shows. These waves are electromagnetic radiation, the same stuff that makes up visible light, infrared, and X-rays. They crisscross our globe, bouncing off satellites, enabling us to connect from thousands of miles away. But even at their breakneck speeds, these signals still take time to travel. For instance, a radio signal to the moon takes about 1.25 seconds, and to Mars, that jumps up to anywhere between 3 and 22 minutes, depending on our planet's positions. Next, let's look at fiber optics, the backbone of our internet. These thin strands of glass or plastic transmit information as pulses of light. They're incredibly fast, allowing us to stream videos, make video calls, and download files in the blink of an eye. But even they aren't instantaneous. The light in fiber optic cables doesn't travel in straight lines, it bounces along the cable, which slows it down. Plus, the cables aren't entirely vacuum and light travels slower in denser mediums, so even the speediest internet connection is still slightly hampered by the speed of light. Now consider the vastness of space. Our fastest spacecraft, Voyager 1, travels at about 17 kilometers per second, a snail's pace compared to light. If we were to send a message to an alien civilization in the nearest potentially habitable exoplanet, Proxima Centauri b, which is roughly 4.2 light-years away, even at light speed, it would take over 4 years to reach them. And another 4 for their reply to reach us. That's a lot of waiting for a simple hello. In a world where time is money and efficiency is key, these delays, however minuscule on terrestrial scales, can become significant. They limit our ability to explore and understand the universe and inhibit real-time interplanetary communication. As we can see, the speed of light imposes certain limitations on our communication technologies. But what if there was a way around it? Stay tuned as we delve into the exciting world of quantum mechanics, where the rules as we know them seem to bend, twist, and sometimes break entirely. Quantum mechanics might hold the key to surpassing light-speed communication limitations with the phenomenon known as quantum entanglement. This counterintuitive concept, which baffled even Albert Einstein, who famously referred to it as spooky action at a distance, describes how two or more particles can become entangled in such a way that the state of one directly influences the state of the other, no matter how far apart they are. Imagine two entangled particles, let's call them Alice and Bob. Alice could be here on Earth, and Bob could be on the far side of the universe. If Alice spins up, Bob will instantly spin down, and vice versa, despite the colossal distance between them. This instantaneous reaction suggests a form of communication that is faster than light. But before we get too excited about instantaneous intergalactic phone calls, let's delve a little deeper. The communication between Alice and Bob isn't as straightforward as it may seem. You see, until we measure Alice or Bob, they exist in what's called a superposition of states, spinning both up and down at the same time. It's only when we measure one of them that both their states collapse into a definite one. So yes, the information about the state change does appear to travel instantaneously, but there's a catch. The outcome is entirely random. We can't control whether Alice or Bob will end up spinning up or down. This means we can't use this phenomenon to send meaningful information, at least not with our current understanding and technology. Moreover, the act of measuring or observing these particles often destroys the entanglement. This is known as decoherence, and it's one of the major challenges scientists face when trying to harness the power of quantum entanglement for practical applications. Yet despite these challenges, the potential of quantum entanglement for communication is too promising to ignore. Scientists are actively exploring ways to protect quantum systems from decoherence and to control the state of entangled particles. Quantum networks, where information is transmitted via entangled particles, are already under development. These could lead to vastly improved security and communication, as any attempt to intercept the communication would immediately destroy the entanglement and alert the communicating parties. While we are still a long way from using quantum entanglement for instantaneous, faster-than-light communication, the journey is as exciting as the destination. The exploration of quantum entanglement pushes the boundaries of our understanding of the universe and brings us a step closer to the next frontier in communication technology. Quantum entanglement opens up new possibilities for communication, but it also presents significant challenges. However, as we delve deeper into the quantum realm, who knows what astonishing discoveries await us. While the potential for faster-than-light communication is exciting, it's also fraught with considerable challenges. The first of these is distance. As we know, the universe is vast, and while light is incredibly fast, it still takes time to travel across such immense distances. For instance, even at the speed of light, it takes around 8 minutes for light to travel from the sun to Earth. Now imagine trying to send a message to a star system light years away. The time factor becomes a significant impediment. Then we have the issue of interference. Space isn't just a vast emptiness, it's filled with cosmic dust, solar flares, and gravitational fields, all of which can affect the transmission of light. These factors can distort or even completely block the signal, making communication challenging. Another significant hurdle is maintaining coherence. In the quantum world, particles can be entangled, meaning their states are linked despite the distance between them. However, maintaining this entangled state over long distances and in the face of environmental interference is a monumental task. Any disruption can cause the particles to decohere, breaking the entangled state and rendering communication impossible. Yet, despite these challenges, the future of light-speed communication holds promise due to ongoing research and advancements. Scientists are continually exploring new ways to overcome these obstacles, and in doing so, they're pushing the boundaries of our understanding of the universe. Take quantum repeaters, for instance. This technology aims to extend the distance over which quantum information can be reliably transmitted. By allowing quantum entanglement to be established between distant points without requiring a single particle to travel the entire distance, quantum repeaters could make long-distance quantum communication a reality. There's also the field of quantum error correction, which is developing methods to detect and correct errors in quantum information due to environmental interference. This could help maintain coherence over long distances and make quantum communication more reliable. And let's not forget about ongoing research into using higher dimensional quantum states for communication. By encoding information into these more complex states, we could potentially transmit more information per particle, increasing the efficiency of quantum communication. In conclusion, while we may not be communicating at light speed just yet, the future is bright. The challenges we face are significant, but they're not insurmountable. As we continue to delve into the quantum realm and push the boundaries of our technological capabilities, who knows what possibilities we might unlock? After all, the cosmos is not just a final frontier. It's a beacon of infinite potential, inviting us to explore, understand, and innovate. Despite these challenges, the future of light-speed communication holds promise due to ongoing research and advancements. But what does the future hold for light-speed communication? Could breakthroughs in quantum communication lead to new possibilities? We're living in an era where the impossible is becoming possible. We're witnessing advancements in technology and science that were once mere figments of the imagination, and in the realm of light-speed communication, the same holds true. The field of quantum communication is particularly promising. One of the most intriguing ideas in this field is quantum entanglement, a phenomenon where two particles, no matter how far apart they are, can instantaneously affect each other's state. Some researchers believe that this could be the key to achieving communication that is faster than light. In fact, China has already made strides in this area. In 2017, they successfully sent entangled photons from a satellite to 2 ground stations over 1,000 kilometers away. This experiment, known as the Mickey's Quantum Satellite Experiment, marked a significant milestone in quantum communication research. But, as with any groundbreaking scientific endeavor, there are challenges. Quantum entanglement is fragile, and maintaining the entangled state over long distances is no easy task. Furthermore, the process of entangling particles and then reading the information they carry is complex and requires sophisticated technology. Still, the potential rewards are worth the effort. Imagine a world where information can be transmitted instantaneously no matter the distance. It could revolutionize not just the way we communicate, but also have profound implications for computing, encryption, and even space exploration. Another exciting prospect on the horizon is the development of quantum internet. This would involve creating a network of quantum computers that can communicate with each other via quantum entanglement. Such a network could provide unprecedented levels of speed and security in data transmission. Yet, it's important to remember that these are early days. Theoretical physicist and Nobel laureate Richard Feynman once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." These words remind us that we're still in the process of unraveling the mysteries of the quantum world. As we step into the future, we're stepping into the unknown. We're pushing the boundaries of what we know and understand about the universe and our place in it. We're daring to dream big, to ask difficult questions, and to seek out answers no matter how elusive they may be. So will we ever be able to communicate at the speed of light? The answer is still uncertain, but one thing is for sure. Our pursuit of this goal is driving scientific and technological progress, leading to discoveries and innovations that are changing our world in ways we could never have imagined. As scientists continue to explore and theorize, we inch closer to the possibility of communicating at the speed of light. So, is communication at the speed of light possible? This question, which we've explored throughout the video, takes us on a journey from the fundamental laws of physics to the cutting-edge theories of quantum mechanics. We began by understanding the speed of light itself, a staggering 300,000 kilometers per second. This cosmic speed limit is a cornerstone of our universe, shaping everything from the stars above to the devices in our hands. We then considered our current modes of communication, all of which are bound by this speed limit. Whether it's a text message zipping through fiber optic cables or a radio wave beaming from a satellite, our communications are always playing catch-up with light. But what if there was a way to sidestep this cosmic speed limit? We turned to the realm of quantum mechanics and the perplexing phenomenon of entanglement, where particles become intertwined in such a way that the state of one instantly influences the other, regardless of the distance between them. Some suggest that this could be a gateway to instantaneous communication, outpacing even light itself. However, as we've seen, the pathway to this potential is riddled with challenges. Overcoming the hurdles of distance, interference, and the sheer complexity of quantum phenomena is no small feat. Yet, despite these obstacles, the quest for faster communication methods continues unabated. Researchers around the globe are pushing the boundaries of our understanding, fueled by the tantalizing prospect of communicating at the speed of light, or even instantaneously. While the goal of light-speed communication remains a monumental challenge, it is a quest that continues to fuel scientific curiosity and push the boundaries of what we perceive as possible in the universe. As we've seen, this journey is not just about faster text messages or video calls, it's about reaching for the stars, quite literally, and reshaping our understanding of the universe.